So today I'll be talking about how to automatically generate test data with Coco and how this will improve the quality and efficiency of your software testing efforts. So my name is James Vance. I'm a software engineer here for the Qt group, and I'm part of the Coco team in Hamburg, Germany. Together with me here as well are my colleagues in the Coco team who will be helping me out in the Q&A portion at the end. So let's first get an overview of what is the main problem that we are trying to solve with automatic test data generation. Human testers and developers often write test cases based on the usual test cases that they know of. This could be the happy path as well as the edge cases based on the tester's knowledge of the code base, as well as their prior experience. However, as the complexity of the code base increases, there is also an increase in the number of parameters, as well as the space of parameters or ranges that need to be tested. This means that you would need to spend a lot more time in order to make sure that you test all possible cases in your software. And we know that many industries require a very high code coverage. Think about automotive, medical industry, defense. They all require the products that they produce are compliant to safety standards. And often one of those is a very high and sometimes even 100% code coverage. The complexity of the code base makes this goal of a high code coverage very time consuming and very difficult to achieve. To address these issues, we introduced Coco Test Engine. It offers a twofold solution to these problems. First, it provides a data-driven testing framework. This means that there is a separation of test code and test data, so that the same test code may be used for several items of the test data repeatedly. And it also enables data-driven testing on third-party unit testing frameworks, such as those that don't have the data-driven testing yet, or those that use a different paradigm for performing data-driven tests. But the second and most important feature of Coco Test Engine is the automatic test data generation feature. As the name implies, this feature automatically generates test data with the goal of maximizing code coverage. And as a result, it also helps find edge cases and error cases that human testers could have missed. And it's able to do this because of the existing code coverage analysis capabilities that Coco already has as part of Coco itself, together with a new genetic algorithm that is used for discovering test data. So let's first recall what a data-driven test looks like. We have here, for example, a function that has an input parameter that is a string and another input parameter that is an integer, and it has an output parameter that could be a double. And we provide as well with this a table of possible inputs together with the expected outputs. And we can have several rows in that table. And the data-driven test works like this. We first fetch the inputs from this table. Then we execute the function that is being tested. In this case, there is the my function. And we verify whether the outputs, the actual output of this function is equal to the expected output from the table. Afterwards, using Coco, we can also measure the code coverage of the data-driven test. So this, or having already a data-driven test, enhances the efficiency of the testing process, since the same test script can be reused for multiple sets of data. But we take this idea of data-driven testing one step further and provide a tool that automatically generates test data to maximize code coverage. So let's first look under the hood first on how this function or functionality actually works. So this is done through what's called the genetic algorithm. It has its name because it is inspired by the biological process of natural selection, also commonly known as survival of the fittest. But instead of living organisms, we consider the test data as our population and the input values to be the genes that evolve over time. So it starts by having or loading existing test data. It is similar to having an initial or a starting population of test items. Then we have a stopping condition, which will be used later, since this will be an iterative process. And we start by generating new input values or creating the new generation of our population. So there are three ways that the genetic algorithm is able to achieve this. First, we can either generate a random value. This is similar to introducing a totally new input into the or a totally new test row or test data into the population. And we can mutate an existing value. So this is similar to mutation that happens in genetics. Or we can also take two values from our existing population and cross over by taking one part of one item and one part of the other and merging them together. So these are the three ways that we can generate new input values. Then we use our data-driven test to execute the test function using the input values and collect the output values. So this forms our test case. But instead of performing or getting the inputs from a table, we instead get it from a generator. And instead of performing the verification or the comparison between actual and expected, we instead store the outputs back into the table as the expected value. Then afterwards, we can measure code coverage, similar to the step before. And then using this code coverage value, we decide whether this new generated input value will be kept or discarded. The decision that is taken to do this depends on two things. First, does it cover a new part of the source code that was not covered before? And second, it also tries to reduce the coverage of every input so that we end up with inputs that cover different parts of the source code. This process or this optimization makes the data also more useful for locating bugs later on. And we repeat this process iteratively, maybe 1,000 or 10,000 times a second. And we try to maximize the throughput and get as many input values as possible. And at the end of this process, we end up with the test data and the code coverage for the test data. So that was how it is done in theory. Now let's see how it's implemented inside Coco Test Engine. So Coco Test Engine has this driver utility, also called Coco Test Engine. It is an executable that will be driving the execution of the discovery of new test data and possibly executing the test as well later on. The requirements for it to discover new test data are the following. So it requires a target executable that is instrumented with Coco. It requires a configuration file and possibly an initial data file. And as a result, it has the data file, which contains the new test data and also the coverage information. So this driver tool drives the execution of this target executable. And this target executable is a C++ script that the C++ file that the user writes and is compiled with Coco. And Coco Test Engine will then be the one to generate the input data and will send this input to the target. The target, on the other hand, executes the test cases and it generates the coverage data. And after doing this, it sends back the outputs to the driver. So the target and the driver have some sort of inter-process communication, since the target is an entirely separate executable and a separate process that the driver handles. Yeah, so let's look at first the target executable, how it looks like, or how the user will be able to write it. So we introduce it is a simple C++ file that performs the logic of the test. And we have some macros that are part of the Coco Test Engine framework, prefixed by the Coco Test. So these macros, this macro, for example, declares a new part of the test logic and calls it test name. And it introduces some macros that are used to fill in this variable called expression with some values from either the genetic algorithm or the test data file. And then after fetching all the necessary variables, those variables are then used to execute the test. the function to be tested, and the result of that execution is collected, and we have some check macros that will verify the result or store the result in the table, in whichever case it will be. So this is the target executable. And on the second ingredient that is needed for test data generation is a configuration file, which shows which lists down the possible input parameters and the corresponding generators involved in creating these input values. So for example, for a string type that we have in the previous slide, we have a generator that is made up of regular expression patterns that satisfy this particular pattern. So these are just mathematical functions that is expected in our parsing function. This means that all the possible generated strings must satisfy this exact pattern. So let's try to see how this looks like in practice. So we have prepared here a demo where we will show test data generation in action. So this make target that we prepared calls Coco Test Engine, and it executes this test cases executable, which was our target executable compiled with Coco, and runs the discovery process with a stopping condition that it executes it for 100,000 times, or it tries to do the genetic algorithm 100,000 times. And now it's trying to find as many rows. So it has currently found 78 rows with a coverage of around 84%. So we're close to finishing. Yeah, so at the end of that call to the genetic algorithm or the test data generation process, we were able to find 79 rows with a coverage of 85%. Now let's look at what the test data looks like. We provide a convenient tool for you to be able to view and edit the test data, and it's called Test Data Editor, and we will use it now to open the resulting test data. So as you can see in your screens, this is the test data that was generated by Coco Test Engine. And if we try to sort it out and see what the results are, we were able to generate some simple expressions in our parser example, with some simple answers as well. But it was also able to generate some complicated values and some complicated strings, which resulted in possible error returns or possible edge cases in our function under test. But they all provided a new path in the coverage. They covered different parts of the source code. That's why they were kept by the Coco Test Engine. Another thing that you might also notice is that there is these parenthesis 0 substring that keeps popping up in all the new results in the subsequent rows. This means that this was possibly survived the mutation as well as the crossover part of the generation of new test data. Yeah. Another interesting thing that we could look at in using with Test Data Editor again is that since we want to since the values or the results that we generated here were automatically generated based on our exact or our implementation of the function, we want to be sure that this input value matches this expected output value according to the specifications of our function and not just our implementation. So that's why we've added also this validated flag, which the user can manually use to check whether the expression that they, or the input values that they have correspond to the expected output values based on how the specification for this function is, and not just how it is implemented. So they can do that, and they can validate all the test rows and make sure that this is correct. Yeah, another thing that the user can also do at this stage is to use Coverage Browser to look at the coverage information associated with the result that we had with test data generation. And this is our coverage browser tool, which you can use to browse the result of your the coverage of your executions. And if we look at the executions pane, we are able to see that every row of our test data corresponds to a row, a separate execution in our executions list. So we can see that the executions have around total or individually range from 6 to 30% in coverage, but overall they increase the coverage to 85%. And we can also use that to look at parts of the code that were not covered or covered and were not covered. So we can see these orange parts are parts of the code that were not covered, the green were covered, and so on. And the red were totally not covered. Then we can continue the test data generation process in the hopes of finding these paths more or better. Or we can also manually add new test data using Test Data Editor to be able to increase the coverage further. Yeah, so that is Coco Test Engine and Test Data Editor. Another feature that the Coco Test Engine has is that if you recall, the execution of the target is done by the driver. So they are two different processes. This means that the driver tool is able to detect when the target executable crashes. And it can also determine which input data caused it. So it's able to report to the user that this row of data caused a crash, and the user can, of course, check or debug their code and find out what caused the crash. Another feature that Coco Test Engine has is the integration with Qtest, CPP Unit, Google Test, and other unit testing frameworks. The only difference is that instead of having a driver tool, the test executable will be written using the unit testing framework, and it will be instrumented with Coco. And there's no driver tool, so the execution of the test data discovery will be done in the same process, and we'll be using a separate configuration file to specify the parameters. This means that it will integrate well with your existing unit testing frameworks, but it means that you will not be able to detect crashes using this, because once an input crashes, then the test executable or the discovery process will also have to terminate. So just some final remarks about automatic test data generation. We saw that it quickly generates unit tests that maximize code coverage. By writing unit tests that cover all possible scenarios and edge cases, this can be very challenging and time-consuming, but automatic test data generation can help fill the gaps in the coverage by generating new inputs that they may not have thought of. And it also helps find edge cases and error cases by determining this using the input data that the user may not have thought of. And it also improves the efficiency of testing a large code base. So this is shown by the creation of the test data, because manual creation of test data can be very time-consuming. And what automatic test data generation does is it speeds up the testing process by producing a variety of test cases quickly. And one of the most valuable and most interesting use cases of test data generation is in code refactoring. So we all know that code refactoring is a very expensive and risky operation. And with Coco Test Engine, you can generate test cases quickly and thoroughly before refactoring. So you can create a sort of a data-based snapshot of the behavior of your application. Then you can execute these test cases continuously during and after the refactoring process to help you find and fix possible regressions. And finally, we also saw that it also enables crash testing. And because this is one of the goals of testing, is to identify situations where the program or the system crashes, and Coco Test Engine is also able to handle those. Yeah. So Coco Test Engine is now available as part of version 7 and onwards. It was released sometime last week. For more information, you can head to this website. And this demo that I presented there's also a detailed tutorial that you can access using this QR code or using the link shown in the screen. Yeah, thank you so much for listening and watching. We're now open to questions. Yeah, so first question we have is, it is not clear how to make sure this input gives the right output data. Okay, let me try to elaborate on that. So yeah, so the inputs that we provide are inputs that were generated by Coco Test Engine. The outputs that is created from this is the result of executing the function under test. This means that the result that you have is the exact result that you would get from the implementation of your functionality of your function. That is why we introduced the validated flag, is because we want to make sure that the outputs that you get correspond to the inputs in your specification. Yeah, second question is, I'm curious about the meaning of coverage. Does 100% coverage mean that all codes have been done? Do I have to check separately whether the result value according to the input matches the expectation? So for the first question, when we say 100% coverage, it depends on the coverage level that you have. So we in Coco, we can do that as low as line coverage. So we can try looking at coverage browser here on another screen. So we can do that using line coverage. It means that all the lines of your code, or it tries to count to make sure that all the lines of your code have been executed. We can also go to decision coverage, which means that every if decision or switch statement, every result of that has been executed, or multiple conditions and MCDC, which are more complex and will look into the different conditions or different combinations of parameters or truth values, for example, as shown here, and make sure that they are all executed. Thanks for the question. There's a second part to the question. Do I have to check separately whether the result value according to the input matches the expectation? So this is a sort of an extra check, an extra manual check to make sure that this allows you to be sure or be more confident that the result that you have was actually verified by human. So it could be that there are some obvious flaws that you can find by looking at it manually, but in the end, it treats, so when you re-execute your test with Coco Test Engine, it will treat differently the data or the rows that have been marked as validated, and make sure that they are marked as successful or marked as a complete failure when the check is performed. It is treated differently to the data that is not validated. So those data that are not validated will have a sort of a doubt or a leeway that they, or a remark that they have not been validated. Next question. Once the refactoring is done, then the inputs and outputs of a function may not be valid any longer. In that scenario, how do you propose to use the previous test data to revalidate the refactor data? Of course, the refactoring that we talked about here are those points where you basically make sure that at least the level of the functions that you want to check are those that remain the same behavior-wise. So this could be applicable more to the functions that are on a higher level on your stack. And if you are, so would be the level of refactoring, or the level of the functions beneath or above the ones that you are refactoring. So if you are, for example, refactoring a function that appears in the user side, then you would like to refactor. Then you would like to refactor instead the functions that are underneath and perform the test data generation to generate the snapshot of those functions that you don't want to, or that you want to avoid regressions. You see, is there support for external systems running on a different PC or embedded system? There's currently no fully tested support for running the target on a different PC, but there could be a way to do that in the diagram that we show here, where, since the target executable and the Coco Test Engine have some sort of inter-process communication between them, then the user just has to provide a way for the target executable to perform the test also on the embedded or the target platform. So the user will have to provide the means for communication between this target executable that exists in the same host system as Coco Test Engine, and send and receive data to the target. But we don't currently fully support that. But in theory, it is possible to be done. About the input validation, this means that the test is not possible to catch if there's an issue in the code itself. We have to do it manually. Yes, you have to do it manually with the validation flag, because it is only the automatic test data generation is only able to capture the current state of your application, or the current state of your program. And that's why you have to, so these outputs are automatically, or are generated from the outputs of your program. So you would have to check whether these expressions indeed match the result. Is there a way to force the engine to use a predefined set of inputs and use only the code coverage feature? So I'm not exactly sure what you mean by this, but if you have a predefined set of inputs, that means that I guess you mean some initial data that you could feed into your test data, into the initial test data. So that is what this initial data file is for. You can provide an already pre-validated set of inputs and their corresponding outputs, and then use that to start the genetic algorithm. Or you can also just not run the genetic algorithm and use this test data to just find the code coverage of this set of inputs. So that one will be the regression testing part, which can be done after the test data generation. Can you provide the tool some inputs that it must use and keep? Yes, so that's another functionality. Thanks for the question. That's another functionality of the validated flag. If you are going to reuse the same data file to generate new test data, or to extend your test data file, those items that have been marked validated are also treated with higher importance. So that means that they will be kept in that data file and will never be overwritten. So that is one way that you can provide some inputs that it must always keep. Is the pass-fail criteria from the test data results certified? We haven't done any certification yet, but we plan to include the testing part, at least, of Coco Test Engine, at least the part that makes the verification of the validation for pass or fail, to be later on part of our tool qualification kit, which a Coco user can run on their system and verify that Coco is used as intended, and also satisfies that can be used also for certification later on. But we don't do the certification directly, but we plan to put it to make it part of the tool qualification kit. Yeah, when a manually validated test case is retested, will a different result be checked and identified as different? Definitely. So when a manually validated test case and you have the corresponding result here, and if the result that you have when you rerun this test later on is different, then it will throw an error. So it will say that this result is different from the expected result. Can I specify the precision for double data? If I change the algorithm during code porting, I could have little different results. Currently, for double data, the precision that we have, if I remember, is still fixed to some value. I forgot exactly what it was. But the good thing is that this part or this value can be customized. Currently, there's no interface to customize it, but you will have access to the source code anyway to run the macros that are used for Coco Test Engine, such as the one used here. So this Coco Test Engine headers will be part of source code that will be shipped together with the Coco installation. So you will be able to control those values, the equality values. Yeah, last question. That means that we can test data one by one manually. If so, does it provide any user-friendly GUI for that? Currently, we don't have any GUI, at least on the level of Coco Test Engine. So the testing process will be done by also Coco Test Engine, and then you will feed a data file. And then it will give you the result of whether every row passed or failed. So it's basically done with any console type unit test framework that's similar to that. So we don't have any way to do it manually by using a GUI. Is it possible to use genetic algorithms for test data with big vector or matrix sizes? That is indeed one of the plans, is to have support later on for possibly instead of just strings and integers, we could have lists as well. But that's still for probably a future release. Is it possible to test graphic applications with a large number of widgets efficiently, either by going through them one by one or by feeding them within a continuous process? So currently we don't really test the GUI applications with Coco Test Engine, or at least it has to be done automatically, or there has to be a way for you to do the testing automatically in this part of the Coco Test test logic declaration. So if you can do that efficiently here and without any interruptions, then it can be possible. But the problem is we also want this genetic algorithm to be executed with a very high throughput. So that's why it is usually more useful to test smaller functions that can be executed quickly in a few microseconds instead of testing a full GUI application in this case. Thank you for attending this webinar. Hope to see you in the next one.